Let's talk about a new concept of lazy learners in machine learning. When you are looking at this video, I assume that you have already have a crisp understanding of about what is linear regression, what is decision tree, logistic regression, and few other models like that. Um, so all those models that we just spoke about, the linear regression and decision trees, these are all eager learners. What basically happens in a eager learner is that you we would be having some kind of a data set. Okay, this data set is divided into two parts. One the 80% and one is your 20%. Okay, so generally the model is getting trained, and we tend to get something like y is equal to mx plus b kind of a model, and then we go and apply this model on an unseen data. So this is how it is getting trained. This is an eager learner. This is an eager learner. So what is typically happening is you're trying to get a trained data set. Based on the trained data set, you're trying to analyze what are the patterns, and based on these patterns, you're trying to apply it on unsigned data and see if the model is robust or not. You're just trying to see what is a error metric in the unseen data and what is error metric in the trained data set. Okay. Now let us talk about lazy learners. These are a different of uh, little different than what we have in the eager learner. Okay. Now what happens in a lazy learner is that it doesn't train. It stays in the memory. Say for example, you have a trained data set, but it stays in the memory. Once the test sample comes, only then the iteration starts. So let us say this is a trained data set, and when I try to apply some model like a lazy learner, one of the example of lazy learner is KNN model. It's nothing but K nearest neighbors. So this trained model, trained data set will be loaded in our memory, and when an unseen data comes, say for example from the validation data, one of the test sample comes, that is when it tries to does the operation. Now the operation could be anything. It can be something like finding the distance, or again in distance we have many things like cosine similarity, or Euclidean distance, or Manhattan distance. There's so many other distances. So the calculation of these distances happen only when the test sample comes. Until then, nothing is done by the model. Okay, we don't have a model until then. So this is memory intensive. Other models are compute intensive. This model is memory intensive. You can go through all the things which I have written in this slide. I don't want to go uh, deep into every point that I have told, but more or less, the only key difference between an eager learner and a lazy learner is that the learner tends to keep everything in the memory, and when an unseen data comes, that is when it tries to start the iterations. Okay, now let us talk about KNN model. Now, this is one of the lazy learner. We have many other lazy learners like SVN, support vector machines. And K nearest neighbor is also one of the lazy learner. Now let us take one simple example where we have a two-dimensional data set. Okay, and all the dots that you see on the right side of the screen belong to one of the class. Say for example, we have class 1 and class 0. Okay, so each of the dot that you see here belong to a particular class. As of now, all of them are black color. It is shown in black color because it is just loaded in the machine. What happens now is you want to analyze you want to analyze for a particular new data point whether this data point belongs to class 1 or it belongs to class 0. Now let us say that the data point is somewhere here in this point. Okay, what happens in K nearest neighbor is you are asking the model to find out K is just a number. Okay, say for example, I put K is equal to 5. So what it will do is it will try to fetch 5 nearest samples from this data point. So this is one sample, this is another sample, this is another sample, this is another sample, and this is another sample. Okay. Now we took these 5 data points. And now what we'll do is we'll try to flip this coin. Like, let us say that this is something like a coin, and then we try to flip it and see what is a class. Say, for example, this data point belongs to class 0. This data point belongs to class 0. This belongs to class 1. This belongs to class 1. And this belongs to class 1. So according to k nearest neighbor, because the majority of this 5 classes are towards class 1, we label this new data point as class 1. Understood? So what we are trying to say is we have to choose the number of nearest samples, and whichever is the majority of the class in the chosen samples, that would be the class of the new test sample. Okay, let's move forward and see what we have. Okay, so what I'll be doing is I'll be taking one test sample here, just as I explained. The circle that you see here is a test sample. I don't know what class that belongs to. Now I want to take 3 nearest neighbors and identify what are the classes of those 3 neighbors. Okay, now I identified that these are the 3 data points which are very near to that new data point. The new data point is nothing but the orange circle, and the old data points for which we already have the classes are within that black circle. Now what we'll do is we'll simply flip these 3 classes. We look at what is the majority of within these 3 classes, and based on the majority we find out or assign the actual class to the test sample. So we are taking 3 samples. After 3 samples, what we'll be doing is we'll try to flip the coins and see what class they belong to. And as you see, one of them is red, 2 of them are blue. So what we'll do is we'll try to assign the blue color to the third test sample. Okay, this is all about k nearest neighbor. Now, because it is based on distances, it becomes more and more complicated as the dimensionality increases. Okay, so you can imagine, like, if it is a 2 dimension or a 3 dimension, the calculation of distance is little bit easier. But as we increase the number of dimensions, say we go to 50 dimension or 60 dimension, the the distance calculation becomes more complicated. Okay, so because we're talking about distances, we have like 4 major distances that we come across. Okay, one is Euclidean, Manhattan, Minkowski, and Hamming. We don't have to go deep into this, but just in case if you want to understand what are the Euclidean or Manhattan distance, you can definitely browse about it. Uh, but more or less, also in addition to this, you also have a cosine similarity. Okay, that cosine similarity generally comes when there are text data. Say, for example, if you want to understand if the word king and queen are similar to each other or not. Of course, they are different, but are they very similar to each other as compared to cat and dog? Okay, so the cosine similarity can put these two, king and queen, very close to each other and very far from cat and dog. Okay, that is what cosine similarity will be helpful for. So because we're talking about k, in the earlier example, we said k is equal to 5 and k equal to 3. Now, choosing k becomes a critical task. We never know which k to choose. Okay, so what we would be doing is just like how we do a hyperparameter tuning in decision trees, where we try to search what should be the depth of the tree and what should be the number of splits and so on. Similarly, in KNN, we can choose the k based on number of values. Say what we will do is, like, for a same given data set, okay, we will try to run a KNN model from the range of say 1 to 11. It can be anything beyond that based on your use case, but usually you would choose odd numbers. Why we would choose odd numbers is because if you take even numbers, like let us say k is equal to 4, if you take even numbers, there's a possibility that you get 2 1s and 2 zeros. So in this case, it will become contradiction. It cannot classify the data sample to 1 or 0 because you don't have the majority class. So that is the reason why you always keep k is equal to an odd number, maybe 5. In this case, if it is 5, let us say that there are 3 ones and 2 zeros. Because there is a majority of class 1, I would say the new test sample will belongs to class 1. Okay. So what we would be doing, how to choose k based on a given sample, or given samples data set is like, we run the model from k equal to 1, say up to k equal to 11, or maybe in this case it is run up to 21, and then we plot the error at what k the error is almost same. As I increase, now if you notice this, as I increase the k value, the error is not drastically getting reduced, it's almost same. So we can stick to k equal to 9 in this case based on this particular graph. This graph is nothing but elbow graph. Okay. What elbow does is it tries to identify a point after which there is no change in error, or the change in error is almost negligible. So choosing k is hyperparameter tuning, and this can be done by grid search CV on k cross validation. I think I can tell you about more about this when we go to the Python session. But for now, this is what we would be having. Okay. Uh, yeah, I think that's it for today's session. I will take one more session on this with Python demo class, and then I can discuss more in detail about KNN. Feel free to leave a comment if you have further doubts. Thank you.